In this lecture, we are going to see the technique 3 for the transformation of random vectors. So again, we try to find out the distribution of g of x given the distribution of x, and we are going to see now the third and the last technique to do this one. And like the previous case, when we discussed the random variable, the same way the third one basically depend on the moment generating function, and in this case we have to talk about the moment generating function of a random vector. So let us first define what is the moment generating function of a random vector. So what was the moment generating function for a random variable? The moment generating function of the random variable defined by that if x is a random variable, either discrete or continuous, we know that the moment generating function of x at the point t is basically expectation of e to the power tx, and we say that the moment generating function exists if this expectation exists if the expectation exists in a neighborhood of origin. Okay, so in case of the random variable, the moment generating function at the point t is nothing but expectation of e to the power tx, provided the moment generating function exists provided this expectation exists in a neighborhood around the point 0. Okay, so the same thing we have taken for the discrete random for random vector also. So for random vector, we say that the moment generating function of x at the point t. Now because x is a vector, t is also a vector, and notice that the number of component in n is same as the number of component in t. And the moment generating function at the point t, at the point vector value t, is same as expectation of e to the power summation ti xi. So it is a direct extension from that of the random variable, because in this case we have one random variable, so I have tx, and now I have multiple random variables, so I have t1 x1 plus t2 x2 plus t3 x3 and so on so forth and the exponent. Okay, so that means that this is a straightforward generalization, and note that if I take n equals to 1, then this becomes the moment generating function of a random variable. Again, the same condition I need to keep here, that provided the expectation exists in the neighborhood of the origin 0. Okay, so in the previous case, the neighborhood that the t was a single dimension, so neighborhood means basically I have an interval, but now I have basically in the Rn, so neighborhood now means either a ball around the point 0 or a rectangle, cube, something like that. So, but I have to but neighborhood in the general sense. Okay, so basically I need to find out a ball around the point 0 inside which this quantity goes to exist. Okay, inside this expectation need to exist, and if that happens, we say that the moment generating function exists. If that do not exist, we say that the moment generating function do not exist. So that means basically if I cannot find out any neighborhood around the point 0 for which this expectation is finite, we say that the moment generating function do not exist. Okay, fine. So the definition of the moment generating function, straightforward extension from that of the random variable case. The same, all the results now you will see that it is basically straightforward extension. So the first theorem talk about the computation of the moment. So in case of the random variable, what we have seen is that if moment generating function exists, then the derivative of the moment generating function at the point t equals to 0, at the point t equals to 0 going to exist, and any other derivative going to exist, and we have seen that this quantity is basically expectation of x to the power r. Okay, so same thing now true in this case also. In this case we have more generalization, that well, if I have x1 to the power r1, x2 to the power r2, in this way xn to the power rn, and if I try to take the expectation of this product, this is nothing but the partial derivative of the moment generating function at the point t equals to 0. Notice that what are the order of the partial derivative? So I have to find out xn to the power r to the power n. So with respect to tn, I have to take the rnth derivative. With respect to t2, I have to do the r2 derivative. With respect to t1, I have to take the r1 derivative. Okay. So and order of the derivative does not change it. If moment generating function exists, it is differentiable it is partially differentiable up to any order, and order of the differentiation do not make any change. Okay, so it is basically again a straightforward extension that from the one dimension. In case of one dimension, I have only one t, so I have to take the derivative with respect to that t, and I have to take derivative up to the order r if I try to find out the rth raw moment. Now in this case, if I want to find out the expectation of x1 to the power r1, x2 to the power r2, in this way xn to the power rn, I have to take r1 derivative with respect to t1, r2 derivative with respect to t2, in this way rn derivative with respect to tn, and finally obviously I need to find out the derivatives at the point t equals to 0, partial derivatives at the point t equals to 0. Okay, so this way I can find out the product moment. These quantities are sometimes called the product moment, so I can find out the product moment in this manner. Next theorem, again it is proof is not given, but very important theorem. You notice that what we have seen before, that if xy are independent, we have seen this one, that if x and y are independent, this implies that expectation of h of x into g of y is same as expectation of h of x into expectation of g of y. Okay, so this particular thing we have seen earlier. Now also we have pointed out that in general the converge is not true. So what I try to mean is that expectation of g of x into h of y is same as expectation of g of x into expectation of h of y for some function g and h does not imply x and y are independent. Okay, and one of the counter example is basically the same example where we talk about that covariance is 0, but x and y are not independent. Okay, so in general, the converge of this one is not true. That for some function h and g, if the expectation of the product of the function can be written as the product of the expectation, that does not imply that x and y are independent. But moment generating function is a very, very special case in this respect, that obviously if x and y are independent, then the moment generating function of x1, x2, joint moment generating function of x and y can be written as the product of the moment generating. This is basically coming from the fact that taking particular choice of the h and g function here, we get that result. Okay, we get that result. But moment generating function is very important and very specific in this respect, that in this case the reverse is also true. That means that if the joint moment generating function of xy at the point t1 and t2 can be written as the product of the moment generating function of x at the point t1 and moment generating function of y at the point t2 in a neighborhood of the origin, then x and y are independent. Okay, so it is a if and only if condition, but keep in mind that this equality has to be true in a neighborhood around the point 0. If it is true for 1 point or 2 points, then this equality does not imply they are independent, but it has to be true for if I can find out a neighborhood around the point origin, or on which the this equality is true, I can tell that x and y are independent random variables. Okay, fine. Now come to the main one, that transformation technique. So transformation technique, the main theorem again same as before, that well, before going into the main theorem, I need to define what we mean by the same in distribution. The definition is exactly same as that of the random variable, that the two n-dimensional random vectors x and y are said to have the same distribution or same in distribution, which we are going to denote by this notation, and they are said to be same in distribution if the cumulative distribution function of x and the cumulative distribution function of y, obviously joint cumulative distribution function of x and joint cumulative distribution function of y are same for all points in the r to the power n. Okay, if in Rn, if for all points in Rn, the cumulative distribution function, joint cumulative distribution function of x is same as the joint cumulative distribution function of y, we say that x and y are same in distribution, or x and y have same distribution. Yeah, okay, fine. And then the next theorem says that if the moment generating function are same in a neighborhood around the point 0, then x and y have same distribution. Okay, and this quantity again, this theorem again we can use in case of, as we have used in case of the random variable, we can use to find out the distribution of transformation of random variables. How we can do that? Well, let us take the example 3.13. So this example is basically, suppose xi's are independent binomial NIP random variable. So x1 has binomial n1p, x2 has binomial n2p distribution, x3 has n3p distribution, and so on and so forth. And we have also taken that the random variables are independent. All the k random variables are independent. Okay. So now notice that when k equals to 2, we have find out what is the distribution of x1 plus x2. Now in this example, we are going to see the generalization of this one, in the sense that, well, instead of 2, I have now general values of k. Obviously k is greater than equals to 2, and I have now general value of k, and I try to find out what is the distribution of summation xi. Again, using the same intuition what we have used in the example 3.10, that we can see that the distribution of y should be binomial with parameter summation ni, I runs from 1 to k, summation ni, I runs from 1 to k, and p. Okay, because again the same intuition goes through, that y is nothing but number of successes out of summation ni trial, and p remains fixed, xi's are independent, so the distribution of y should be binomial, with summation ni k distribution. Okay, let us try to prove this using the theorem 3.19. So I try to find out first what is the moment generating function of y. Notice that in this case y is a random variable, so moment generating function of y at the point t is a scalar, at the point t is nothing but expectation of e to the power ty. Now I just plug in the instead of y, I just plug in the definition of y, and then we know that expectation e to the power summation is same as the product of e to the power. So using this, I can write that expectation of e to the power t summation xi is same as expectation of product of e to the power t xi. Now because xi's are independent, and if I take gi functions are e to the power t xi, then basically expectation of product of the function can be written as the product of the expectation. Okay, because xi's are independent. So it can be written as product of e to the power, product of expectation of e to the power t xi. And notice that this quantity is nothing but the moment generating function of xi. So this whole thing is nothing but product of moment generating function of xi at the point t. Okay. Now I know what is the moment generating function xi at the point t because xi has a binomial ni p distribution. So for a binomial np distribution, the moment generating function is 1 minus p plus p to the power t whole to the power n, and moment generating function exists for all t belongs to R. So the moment generating function of y is nothing but the moment generating function of xi, and the moment generating function of xi is nothing but 1 minus p plus p to the power t and to whole to the power ni. Now I have a product that will give you, because this quantity is fixed for all I, so that product is going to give me this quantity to the power summation ni. Okay. Now notice that if I have a random variable j which has a binomial summation nip distribution, then the moment generating function of z is exactly same as this quantity. Okay. So that means the moment generating function of z and the moment generating function of y are same for all value belongs to R. So that implies that the distribution of y and distribution of z are same, and because the distribution of z is this one, so that means the distribution of y is also binomial summation nip. Okay, clear? So I hope this example is fine. So the again our idea is basically same as that we have used in case of the random variable. That first we need to find out what is the moment generating function of the transformation, and once I get the moment generating function of the transformation, I need to identify that for which distribution this is the moment generating function. Obviously in this case this thing is very simple, because again the final one is exponent, the final one is binomial, belongs to the same family, but sometimes if the family changes, that the distribution changes, I need to basically understand that the resulting moment generating function corresponding to which distribution. Okay, fine. Let us take another example. In this case, I have x1, x2, xk are IID with exponential lambda distribution. Again, I try to find out what is the moment generating function of y. We proceed in the same way that we try to find out the moment generating function of y. Again, it can be written as the product of moment generating function of xi. Now, because all the xi's are same distribution, so the moment generating function of all the xi's are same. So this product can be written as the moment generating function of x1 to the power k. And we know that the moment generating function of exponential lambda distribution is nothing but 1 minus t by lambda, and it exists for all t belongs to lambda. So when I take to the power k, it becomes 1 minus t by lambda whole to the power minus k. Okay. So that now I need to understand for which distribution this is the moment generating function. Now you see that if I take z follows a gamma distribution with parameter k and lambda, then the moment generating function of z is exactly this one, and the moment generating function of z exists for t less than lambda. So that means that the moment generating function of z and y are same, and this shows that y has a gamma distribution with parameter k and lambda respectively. Okay, fine. So same way you will be able to do the example 3.15. In this case, our distribution, the random variables are independent, but they are not identically distributed. That x1 has normal mu1 sigma 1 square distribution, x2 has normal mu2 sigma 2 square distribution, and so on and so forth. And again, suppose we try to find out what is the distribution of summation xi. And in this case, using the exactly same technique, you will be able to show that the moment generating function of normal of summation is nothing but again normal with mu with summation mu I, parameters are summation mu I and summation sigma I squared. Okay, so I leave it as an exercise. Please try to do this one. The technique is exactly same as previous two examples. So just try to do this. Okay. Now we are going to see two more definitions, and then I will stop. So the first definition is basically the expectation of random vector. Remember that when we talk about expectation of random vector, then we basically talk about expectation of function of random vectors. And in this case, we basically talk about the expectation of a function h, which is a function from r to the power n to r. So we basically talk about a function h, then we talk about expectation of h of x. Okay, that's what we talk about. So now notice that because h is a function from Rn to R, that means h of x is again a random variable. Okay, so h of x is again a random variable. Is a random variable. Okay, so still now, whenever we talk about expectation, we basically talk about the expectation of a random variable, not a random vector. So we now try to talk about the expectation of random vector, and the definition of the expectation of random vector actually comes from the expectation of random variable. So what we do, that expectation of x, suppose x has n component x1, x2, xn, expectation of x is nothing but we take the component wise expectation. So expectation of x is nothing but the vector consists of expectation of x1, expectation of x2, expectation of x3, so on so forth, finally expectation of xn. Okay, so it is basically component wise expectation we take, and that was we call that expectation of the random vector x. Okay, and normally we denote it by mu. Obviously bold we have used to make sure that this is a to indicate that this is a vector. Okay, similarly, that when we talk about the variance of a random variable, we talk about covariance of two random variables. Now we try to generalize it for a random vector. Suppose we have again n-dimensional random vector. Then we have a variance covariance matrix, which is nothing but consists of which is nothing but a matrix sigma. Sigma is a n cross n matrix, which each components are basically nothing but variance or covariance. Okay, so how do we arrange this? The arrangement is quite simple. So sigma, which is variance covariance matrix, is nothing but, you can think of this way, it is the covariance between x1, then covariance between x1, x2, so on we go. Finally, covariance between x1, xn, then covariance between x2, x1, covariance between x2, x2, and so on and so forth, covariance between x2, xn, and so on and so forth. Final column will be, so final row will be covariance between xn, x1, covariance between xn, x2, and the final entry is covariance between xn, xn. Okay, fine. So this is a n cross n matrix where we arrange. This is a n cross n matrix where we arrange the covariance, and it is very easy to remember because you just think of 1, 2 up to n, 1, 2 up to n. You just take kind of a cross thing that it is a covariance between x1, x1, covariance between x1, x2, covariance between x1, xn, and so on and so forth. Now notice that this quantity is same as variance of x1. This quantity is same as variance of x2. This quantity is same as variance of xn. Okay, so that basically means that the diagonals are basically variances. First diagonal is variance of x1, second diagonal is variance of x2, and so on and so forth. And of diagonals are covariance. Okay, so this particular thing is called variance covariance matrix, and you can easily take that this can be written in this form also. Just you take the product, take the matrix product, but first one is column, second one is row. So sorry, first one is column, and second one is row. First one is column and second one is row. So that means when you take the matrix product, it will give you the matrix, and then when you take the expectation of a matrix, again you take the component wise expectations, you will basically going to get exactly this particular this particular matrix. Okay, with that I stop. In the next lecture, we are going to see a new concept which is called the conditional distribution.